Hey Calc class, happy Asyncy Devinky Day. So first of all, just wanted to say as you're watching this, I recommend going down to the bottom, clicking on the three dot or the gear and making the playback speed 1.5, 1.75 times or 2 times because I know I could speak slowly. I personally like doing that with Salcon too, but I'm excited to get a chance to look at some of these problems. Oh, I think in one of the breakout rooms we also solved the mystery of the YouTube view count. I think it's because it was posted on Classroom. Some of you were watching it right in Classroom, so it wasn't taking you to YouTube and therefore wasn't registering as a view. So that made me feel better. But um, what I'm going to do today, so we went through the example for A there. But I want to walk through the rest of these, and I'm excited because these ones are quite fun. I think so, and it's going to relate to your practice for today. So now thinking about how we could interpret and apply these ideas of the derivative. So again, if you're having trouble finding the derivatives, actually at that Paul's Online Math notes, you may notice I've been working actually right from it. Many of the examples are the same. Like I find it to be a great resource. Let me do this so you can see the navigation. So if you go to calculus, you can see there's derivatives. We started with the definition of the derivative. These are the derivatives we found, right, on the first day. And the nice thing is you could show solutions. You could even, there's somewhere you could show all solutions. I don't see that. These are the practice problems you had for homework. All the solutions are there. And this one's not as, oh, some of these are better worked out, I think. Oh yeah, show all steps. It'll show you all the steps with an explanation. I really like this. Also, if you, and then what the examples we're doing are now in the next section. Oops, so now we're interpretation of the derivative. I don't always just use this website, but I found it to be quite helpful. So these are the practice problems I'll assign today, but here are the examples that I'm about to work through here. So we did the first one, we used V of t. And remember, this is sort of thinking about the rate of change. So the rate of change of the volume. We just made up gallons because they didn't give us, one annoying thing is they didn't give us the units. So for B here, is the volume of the water in the tank increasing or decreasing at t equals 5 minutes? Well, it's kind of simple actually because all we're doing is plugging in 5 here. Since we have the rate of change equation, aka the derivative, I could just plug in 5. So I get 4 times 5 minus 16. This will be positive, so it's positive. It'll be a positive 4 precisely. So we could say yes, positive for B. C, these are all the ones you did in class. Is it changing faster at 1 or 5? Well, it's an interesting thing. The volume now, if I plug in 1, so this would be 4 times 1 minus 16. So the rate of change at 1 is negative 12. So negative 12 gallons per minute at 1 minute. And then at 5 minutes, we already did that. It was, well, I didn't finish it, but it was at 4 gallons per minute. So in this case, I think we'll actually say at 1 minute, it's changing faster. It just happens to be changing. It's losing water rather than gaining water, right? So at 5 minutes is actually filling up, and then at 1 minute it's losing, but it's losing it 3 times as fast as it's gaining it at 5 minutes. Is losing water faster than gaining at 5 minutes. So hopefully that's a pretty good explanation. And then this last question is an interesting one, and this is one of my favorites in this first part is because that forces you to think a little bit strategically. Is the volume of water in the tank ever not changing? If so, when? So, if the water is ever not changing, that means the rate of change would have to be zero. So we could use this V of t equation, but we're basically replacing this and see, is there a t value that would give me zero? Well, let's try it out. Interesting. So I could think, well, I could now try to solve for t. So let me insert a bit more space. I didn't insert enough before. And I would have add 16 both sides. Some of you may already just see the answer. Divide by 4. Well, at t equals 4, we have a 0 or a root of the derivative. So it means the rate of change at time 4 is 0. So we could say at 4 minutes, the volume is not changing. And what that means is that's the spot where if we were looking at the volume, that would be like a maximum or a minimum. The curve of this original function, this one, oh, I guess that would be the vertex of the parabola. So that would be like this spot. But on this graph, it's going to be the 0. It's going to be where the derivative line hits the x-axis, wherever that might be. Interesting. Find the tangent line. So this one threw off a few people. Shout out to, I believe it was Quinn and Jasmine. Yesterday we were discussing this in one of the small groups because it came out to be a little messy, but that's okay. So if we look here, find a tangent to the following function at z equals 3. And Jasmine has said, well, couldn't we use point slope form? And I think that actually would be quite helpful. You could use slope intercept. There's nothing wrong with that. And it doesn't say to get the tangent line in any particular form. So if you remember this, we get y minus y1. I hope I get this equation right. X minus x1. So I need an xy relationship for the function to find actually the point that it's passing through, which would be that one tangent point to the curve. Probably like right there. That wasn't a perfect drawing, but you get my sense. I'm going to have to get the slope at that x value. That's not too bad because I'm just going to find r prime of 3, which will give me the slope of the tangent. R prime of 3 will be 5 over 2 times the square root of 15 minus 8. So this is what Quinn was saying, Mr. Tannen, this is not too pretty. Well, I have the slope of the tangent line though, that's okay. I can have roots in there. I'm not going to get the roots out of the basement. I know we used to like to do that in Algebra 2, but we'll just ride out with that one for now. Now all I really have to find is that point, so I'm going to have to use the original function to find a point on the graph. So plug in 3, that'll be, well, just root 7, because 15 minus 8 is 7. So the point y1, oh sorry, x1, y1, oh my gosh, you got to be kidding me with that one. X1 would be the input, which is 3 and then root 7. So now I think I've got all this info for point slope form. I get y minus root 7 equals 5 over 2 root 7. And then x minus, 3. The x value is 3. Rewatch that if I went too fast, but then Jasmine was like, well, point slope form, that's a perfectly fine form. It didn't say to get in a different form. I mean, I could distribute this and get the y by itself if I wanted, just add this over. I mean, but we did the calculus and we did the understanding and interpretation, so why not just leave it like this? Oh, we could check what the what form young Paul did for this one. I didn't check the answer because I was just feeling so confident in our work. Oh, he left it basically the same. He just added the root 7 over to get the y by itself. So that's okay. All right. Suppose that the position of an object after t hours is given by this. Answer both of the following about this object. Okay, let me check this out. Uh-huh. Oh yeah, I think we had gotten this derivative. So the position, so basically if the position is represented by that, we could represent the change in the position, or basically the movement, with the derivative. So I think we got that derivative back here, way up here. Where is it? Oh, is that 1 over t plus 1 squared? Bada bing, bada boom. So let's write the derivative because you see all of these. We're using that derivative. I can't come up with a good rhyme with derivative. Somebody, Maeve will probably come up with a good rhyme for us, like she did with Asyncy Davinci. Oh, I hate it when it does that. Why is everything else? It's like one part I wrote just didn't stick onto the OneNote. Come on, OneNote, get your act together. Oh, now you got some weird shadows going on. Holy mackerel. Excuse my language. Let me, oh my gosh, this is frustrating. Nick Frustraterson. Answer both of the following. So, is it moving to the right? So in this case, I think moving to the right versus the left would be positive or negative. Plug in 10. Well, it's still going to be positive, right? And would it ever stop moving? That's a good question. I think, well, I think it isn't ever going to stop moving. It's going to, I mean, as t gets infinitely big, I mean, we're assuming there's no negative time, right? As t gets infinitely big, we can see that it's going to get slower. It's going to be moving slower and slower because the limit as this approaches this is going to be 0. If this were a limit as t approached infinity, it's approaching 0. But because it can be infinitely slowly moving, I don't think it's ever going to stop. So I think we would say yes here, and we would say no here. Let's see what Paul said about this one. Come on, Paul. I hope we got it. So it is moving to the right because it's positive. Right would be when the velocity is positive, left when it's negative. The object will never stop moving, so we're correct. It's never going to stop moving if the velocity was ever 0, but there's no way a rational expression will ever be 0. Exactly right. Thank you, Paul, for confirming. Okay, so I had to pause. Sorry, to see if I could get my OneNote to work a bit better. I hope it did. So, all right. So this is, like I said, a pretty fun one. So if I have a sketch here, so you see how the slope here is very negative, but it's slowly getting less negative until the slope here would be a 0, right? And then the slope becomes positive. So one thing that's helpful when sketching these is I know the derivative has to go through 0 there. And then the slope would be positive, and then it's got a 0 up here, right? Because it flattens out again. So I know there. Everywhere I have a maximum or minimum, my derivative is going to have to be 0. It seems like kind of right here too, it flattens out. This is more of what we would call a inflection point, where it goes from increasing to decreasing. But see how it's sort of flat? Like it seems like it gets to a slope of 0 and here. So now we see the slope is very negative. So let me do this. And then the slope is becoming steeper up until about here, I think, where it starts becoming more the slope gets less steep here until finally the slope gets to 0. And then the slope is negative. But that last part was not too good. Slope is negative and it flattens out, and then